NASA, this is Jay Tolan.
Yes, sir.
I'm calling to report an incredible scientific discovery. You won't believe this.
What is it, sir?
I applied photogrammetry to your orbital footage of the Earth.
Is that right?
Just incredible imagery, and I was able to turn that into 3D models of the Earth's surface.
Is that right?
And when I measured the curvature of these models, I was just blown away. What I discovered is that the curvature of the Earth is about 3 to 4 times larger than what we previously assumed. I mean, the Earth is practically flat, and this is incredible. Hello? 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 Are you still there? Hey, how's it going, everyone? Let's apply photogrammetry to orbital footage of the Earth. Incredible results, and also the moon. Watch this. This is incredible. To introduce photogrammetry, let's apply the technique to the Cayuga spacecraft imagery.
In front of the Kaguya, as it travels down to the south in the high latitude area of the northern hemisphere, the Pythagoras crater comes into view. The Pythagoras crater has very
You can find a number of video clips from the Cayuga spacecraft. It has 3 main instruments according to the documentation, the main one being the HDTV camera, which is what's producing these clips. And it's quite fascinating to, dig through all these documents. They give you quite a bit of information. So here's a flight over Aristarchus crater coming up here, and I will take different snapshots from this video and put them into meta shape. So here I have created a 3D model of a patch of the lunar surface from the photography. And this photogrammetry algorithm is pretty powerful. It not only finds out exactly where the cameras are, as you can see right there, the blue squares, those are the locations of the cameras, okay? So I just took a few snapshots from that video clip you saw and put them in meta shape, and then meta shape does all the calculations, the photogrammetry. Okay, so now let's turn off the cameras and create an animation. So this is a very nice feature. You can just click a button and it will rotate the model so you can get different perspectives. Just incredible. I mean, if you think about it, the spacecraft went only one way, but now we can rotate and look in different directions. So that's the power of these, computer tools that let us visualize, the surface models. So, yeah, pretty powerful technique, and we'll apply this to the Earth. There's plenty of orbital photography of the Earth. Now let's build a model of northeastern Africa from one of the ISS overflights that we saw in the intro. So here you can see the model, and it takes quite a bit of effort to clean it up. There's different points. You create dense clouds. Now here is the path of the ISS, and you can see the location of the frames that were used to create this model. By comparing the model with a map, we can size up the dimensions and figure out length, and that's useful. The size of the model here represents about 1,250 miles by 600 miles, so a pretty large portion of the Earth's surface. One of the first measurements I made was to measure the altitude of the orbit above the surface, and this is a little bit qualitative from this particular angle. The altitude is about 300 miles, but the official is around 250 miles. Here I measured the orbital path curvature. In the lower right, you see the equation, length of the chord, height, etc. And when we plug in the numbers, we get about 3,600, thereabouts. But what's interesting here, if you look at the model, the curvature seems to be around 2,500 miles. And I came to the conclusion that that's due to the lensing they're using. Because when we look at a different direction, it comes out to a different number. So there's some strangeness here. So when we look cross track versus along track, we get to different numbers, almost a factor of 2. And that's really because of the lensing, the lens that they're using in these cameras. It's throwing off the calculations, but not all of them, which is very strange. Another curious observation is the orientation of the camera at about 45 degrees off of the direction. But the most curious thing is, notice the flight path when looking from on top curves towards the north. Whoa, this is bizarre. So why is the ISS flight path curving towards the north after it crossed the equator? We're gonna find out soon enough. Check this out, folks. This is just incredible. When we measure the curvature looking from on top, it comes out to almost the radius of the Earth. What is going on, and how come it's curving that way? This is very strange. And let me say this, it violates the globe. This is just incredible, folks. The globe and orbital dynamics cannot explain this strange curvature. Now in this graphic in yellow, I showed the ISS orbital plane. Okay, and if you talk to experts, the way it works, the satellite, in this case the ISS, goes round and round and round in this orbital plane, and the Earth underneath rotates. So the ISS is in its own inertial frame of reference, okay, and the Earth rotates underneath. And so that's why you see this oscillatory orbital path on the Mercator maps, okay? And here I'm showing the globe perspective. So this strange curvature towards the north is very curious, and as you'll see in the end, it's perfectly explained by the flat Earth map. But before we move on, have a look at this new model derived from the same photos. I actually found the trick. Wow. So let's have a look at the United States. I searched YouTube and found a very nice clip where the ISS traverses across the US, as you can see here. And it represents quite a bit of curvature. So let's see how the model comes out. The weather that day was excellent. This is an excellent video clip. Look how clear it is. And I put a mask. I want the software to only focus on the lower left corner where there is a more direct, straight down look for higher accuracy. As it moves north to Canada, you can see a lot of cloud cover. So we'll truncate the model. Now here's the model, and let's turn on the camera so we can visualize the orbital path, and we can see some curvature which we'll measure shortly. But also, if you look carefully, there appears to be a higher accuracy zone and a lower accuracy zone. because of the coverage. So to the left we have extremely flat terrain, and then it curves away. Here's why this phenomena is occurring. So we have a high accuracy zone on the left due to a larger baseline, and a low accuracy zone on the right side because the photos end. So here's why. As you can see, the larger baseline gives you very precise distances to points on the surface, but when you look out skewed towards the horizon, the projection of that baseline, the true baseline, is very small, and the inaccuracies increase rapidly, and that's where the lensing that they're using plays a bigger part and skews the model. Now I've also applied the mask only to the right side. I tried different masks and also in the center, but it seems that the results are pretty consistent, and that's encouraging. So here's the model, and here I finished this model up, added texture and other things, and it's very smooth, just like before. You can also see the orbits. So if we turn off the cameras, look at that. This is incredibly flat, folks. Wow, look at that. Yeah. Here I'm moving it around. Now let's rotate it. Whoa. That is incredibly flat. So we'll do some calculations on this shortly, but first we have to determine kind of the distances that we're dealing with, and we'll use the map for that. So here's the 3D model superimposed on an image of the globe, so we can identify features in the imagery and derive distances so that we can measure the curvature of the surface. So what is the radius of the Earth? Well, to help me determine that, I put a spline and I fit it to the surface, and then I drew the chord, okay? And I'm using that formula in the lower left, okay? And the results are pretty incredible. So let's do the calculations. Okay, so let's bring up the calculator here and crank some numbers. Okay, so we have 2050 for the chord. We'll square that and then divide by 8 times the length of the height below the surface, which is 35. Okay, and it's about 15,000 miles, and of course we can add the small h/2 contribution, but the radius of the Earth is a whopping 15,000, almost over 3.5 times the accepted radius of the Earth. This is just incredible, folks. I've been on YouTube for about 10 years, and this incredible result finally validates what I've been observing in infrared. I've been flying over the US, and I've posted a number of incredible images taken from aircraft. It appears the United States is extremely flat, and now we have proof from on high, which is very encouraging, but at the same time this is troubling. I mean, you know, the radius is just way too large. There's a problem here.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Liftoff of Falcon 9. Go SpaceX, go Cosmo.
In March of 2024, the Sun Corporation sent up a new payload with 4K cameras. The payload has three main cameras pointed in different directions. Their hope is that we will be inspired, and I certainly have been inspired. Now, let's have a look at one of the cameras. This new footage has two important features. First, it is high resolution 4K, and second, it has the capability to pan and tilt, which is what we're seeing here. And this is very important. For the first time, we can see that the extent of the view is not as large. Okay? We can see, like right about now, we're actually looking straight down. And I've been saying this for a long time. The curvature we're seeing is due to the lensing. It is not the true curvature of the Earth. The Earth is not just the Sinai Peninsula. Here I'm playing the same clip, front to back, and then I reverse it. Okay, so they're not actually going back and forth like that. But what we can note is that it appears we're not really moving along the orbit, and that's because the pan and tilt is very drastic, and it swaps the slight movement of the International Space Station. But the movement is there, as we'll see when we attempt photogrammetry. Also note the intense glare of the Red Sea. This is kind of problematic for the model, and we'll have to clean it up a bit. But before we move on, we have to mention some interesting facts and historical sites in this field of view. The most famous is the Nueva beach, where the Hebrews encamped before they crossed the Red Sea. Wow, look how clearly you can see it. It's pretty large. And they crossed into Saudi Arabia and went to Mount Sinai. That is the true location of Mount Sinai. It is in Arabia. There's videos online if you're interested. The discovery of the Red Sea crossing is attributed to Ron Wyatt. He studied the Bible and the accounts, and it says that they were enclosed by the wilderness and trapped, and he did a lot of work, and then he went scuba diving off of Nueva Beach and found chariot parts and hoofs, and just incredible work, a man of God. But his prior claim to fame was the work he did in Turkey to identify the remains of Noah's Ark. I met Ron Wyatt in the 80s, and I bought one of his books, and he signed it for me. Very godly man. And of course, the greatest discovery was the work he did in Israel around Golgotha. He actually discovered the shafts that lead down to Jeremiah's grotto, which is inside the mountain, where the Ark of the Covenant was hidden. And I just get chills when I talk about that, because I was in the audience when he presented the actual footage. I never felt the presence of God like I did on that day. You know, there must have been over 1,000 people in this huge auditorium at a university, and he was sobbing, and the imagery from the Ark of the Covenant had some sort of a distortion due to the radiant presence that's around it, and not even Kodak could explain why that was occurring. He took photos, but the video would turn in such a way strange graphical effects, and this was in the 80s. So anyway, it was so impressive. Children to adults were just like sobbing. The presence of God was felt in that auditorium. Now let's continue with our photogrammic analysis of this incredible imagery. Now here's the photogrammetry results. An extremely flat patch of the Earth again. Very interesting. look how flat it is. I mean, we can see the topography. There's obviously variation due to the mountains, the features, geographical features. But overall, this is incredibly flat. Look at that. Just incredible, folks. Here's a closer view. We can definitely see the mountains in Mount Sinai on the left, and then over there the old Mount Sinai in the Sinai Peninsula. Isn't that strange? Yeah, right there in the center is Mount Sinai in the Sinai Peninsula, and over there is the real Mount Sinai. Just incredible. Just blew my mind. So this is a top-down view of the model, and I added these concentric circles to kind of hide the jagged edges at the edge of the field of view. This graphic kind of illustrates what's really happening here in the angles. You see the International Space Station is fairly close to the Earth, and when you look out, you hit that blue haze and the edge of the horizon, but due to the lensing it makes it look like that's the curvature of the Earth, which is not. And there in the inset you can see, as I've been saying all along, the Earth they're showing is very tiny. Okay, here about 700 miles in diameter. That's all. So it's not really the globe, it's just lens artifacts. Here's another perspective that illustrates the pronounced curvature we should be seeing if the Earth was really a globe. I drew out those horizontal lines to the edge, so we should see quite a bit of curvature, and we don't. Now here's a qualitative comparison of curvature, okay, comparing the globe and the photogrammetry model, and you can see the glaring difference between the two. Notice in Google Earth that I am at about 400 miles altitude. So what is the true radius of curvature of this model? It's obviously way larger than the accepted value. So let's do some calculations. So like before, I am putting an approximate spline to the model and then a straight line, which is the chord. And I will use that equation that I showed before. So when we carry out the calculation, we get again this incredible result of 15,000 miles. Isn't that incredible, folks? Wow. But over 3.5 times what we think the radius of the Earth is. And if I adjust the spline slightly to the middle of the topography there, I get about 12,000. So anyway, it's certainly 3 to 4 times larger than the 4,000 mile radius that we currently believe is the correct number. So just incredible results, folks. Okay, so finally let me introduce you to an incredible map of the world. Since pretty much everyone in academia knows we live on a globe, they try to make projections of that globe, and there's different projections, as you can see here: cylindrical, conical, planar, and they have different attributes. For example, conformal projections may preserve local angles but probably screw up on the distances and areas. As you can plainly see, the land masses look pretty strange. The Mercator projection is well recognizable by many people. It's one of the main projections being used. But of course, it has its issues. Apparently, distance between 2 points is not correct. The Great Circle route is actually a curved path. And then, of course, the areas of the of the land masses towards the north are really skewed. You can see Greenland there, it's super huge, bigger than the United States, when Greenland is actually a fraction of the United States. The azimuthal projection preserves correct directions, but only from the center. Now here's an interesting map projection, the genomonic. It claims that all straight lines drawn on it represent great circle routes. Okay, looks very strange. There's even strange demonic looking maps. Oh, I'm sorry, it's a star. I found this very interesting sentence here from Penn State, Cartography and Visualization. Look at the first sentence there. From a young age, we are generally taught that Earth is a sphere. Images such as those taken from space, etc., reinforce this idea. Yet this is an oversimplification. Earth's actual shape is far more complicated as it appears to be. Whoa, that's interesting. Now, don't get your hopes up. These people are not flat earthers, quote unquote. Okay, they're talking about the Earth being slightly ellipsoidal due to the spin, etc., right? And they're saying it's actually an oblate spheroid. But the difference between A and B is so slight, it's practically a sphere. They have an interesting graphic of the geoid. Of course, it's exaggerated. Okay, and then the Earth's surface, there's this imaginary ellipsoid, yada, yada, yada. Now, if you want a really good practical map, the Air Force, not the Space Force, has the answer. Here's a photo from the Strategic Air Command headquarters, and there's videos online too. And they have these maps because they had nuclear bombers up in the air all the time, ready to strike. And you can see in the left photo the black lines there. And this map is very interesting, very interesting. Look how small Greenland looks. All right, it is practically the size of California and maybe Oregon. So yeah, this got me very curious, and I did some digging, and then I found one of the best maps that they have created. Here it is, folks. The Air Force has put together such a beautiful chart. And look at it. It kind of resembles an azimuthal equidistant map for the Northern Hemisphere. But then they fixed the distortions of the land masses as well. Very beautiful. And curiously enough, they claim that they've solved all the projection issues of angle, distance, and size, which is incredible. I kind of felt intuitively that this should be possible, and sure enough, that's what they claim. So I've highlighted the small text that's barely readable. I have a really high resolution image and I had to zoom in. But this is what he says. The polar stereographic projection used for the Northern Hemisphere provides the best possible map representation of global relationships for an area as large as a hemisphere. Wow. And then it continues. The conformal property of this projection produces true geographic shapes, true directions, and permits, get this, excellent distance measurements. Wow, that's incredible. So let's revisit this mysterious curvature towards the north. One of the first things I did when I learned the Earth was flat was take the ISS path as is shown at the top on the right side and transpose a few points onto the azimuthal equidistant map. and we get a circular path. Now, here's the same technique applied to this new Air Force map. Have a look at this, folks. Here we can now clearly see the curvature towards the north. So these equidistant, azimuthal equidistant maps, or whatever this thing is, seems to have a leg up on explaining the orbital path of satellites. Isn't that incredible? The globe fails, but yet this map explains things better. So what if the globe is an illusion? In conclusion, folks, I love mysteries, and this is a graphic I put together a long time ago. Basically illustrates the dilemma we're dealing with. When we look up above, we have a solar system model. Everything checks out pretty much. When we look down below, it appears the Earth is flat. And whenever there's incompatible ideas, it's a great opportunity to learn something new. The view of our world from space is breathtaking. Our world is very beautiful and colorful. However, capturing a wide field of view with fisheye lenses is leading to the wrong conclusions and perceptions on a monitor screen. Okay, there's a limitation there. This is the true view from space, folks. Have a look at these images. This is a view of the Cygnus spacecraft by Northrop Grumman that was sent to me. Very beautiful. But the most beautiful images come from the Chinese space station. Have a look at these images, folks. The Earth is truly amazing. Behold the flat Earth, folks. Truly incredible. Thanks for watching, everyone. Happy New Year!